Good afternoon, everyone. My name is Harshit Tiwari and I'm a PhD student at the Department of Physics, IIT Kanpur, and I'm working under the supervision of Professor Mahendra Verma. And I will be presenting the title of my talk is Classical One-Third Nusselt Scaling in the Compressible Convection at Extreme Rayleigh Numbers. The main motivation of my talk is how does the momentum and heat transport depends at these extreme parameter, this Rayleigh number, when the compressible effects are also important. And these kind of large systems shows these extreme Rayleigh number. So for example, this solar convection has Rayleigh number of the order 10^22, and also in the atmosphere, in the troposphere, the Rayleigh number can go as extreme as 10^24. So my main focus is to see the scaling of these global quantities, the Nusselt number, which is the total flux divided by the conduction flux, and it is greater than 1 when there is a convection. And also this Reynolds number, how does it vary with Rayleigh number? And this brings me to another point, that when we take a sphere, flow past a sphere, so around 10^6 Reynolds number, we see a transition where the boundary lets become turbulent, and there's a sharp increase of drag and also the heat transport. So does the similar thing happen in this convection in a box? So we wanted to see that. So this is known as the ultimate regime. So in the literature we have some of the scalings. So Malkus and Spiegel, they predicted this classical 1/3 scaling for lower Rayleigh numbers, and also for Reynolds number, this is around 0.5 half scaling. But Kriegman predicted that at very high Rayleigh number, this Nusselt number will go as Rayleigh to the power half, which is also called as ultimate regime. And similarly, the Reynolds number also goes as the Rayleigh power half. And these are some of the works in literature. So some of the people like Chavan, Roche, Pietel, Zhu, they observe the ultimate regime, and there are also some people who do not observe the ultimate regime. And in the simulation, people have reached, like for 2D, highest Rayleigh number is 10^14, and in 3D, the highest Rayleigh number is around 10^15. So we wanted to simulate this kind of system. It is a very ideal system, which is a box, Cartesian box, which is heated from bottom and cooled from top. And here there is no approximation in the density, so it is fully compressible. And the boundary conditions are periodic horizontally and no slip in the top and bottom. So I have written the conservative forms of equations. So this is the continuity equation, this is the momentum equation, this is the total energy equation, and these are all, there is a pressure equation in this. So this is the ideal gas law, and here the viscosity is also there in this stress tensor, and the total energy has the kinetic part, the thermal part, and also the potential part. So the criteria for convection is, so when we consider the hydrostatic and thermal equilibrium, we get a static linear temperature profile. So this is the profile, and at the same time there is a density profile, and this density profile has a polytropic index, which is given by this. And if we also consider in this equilibrium the adiabatic process, we get another linear profile where the gradient is adiabatic gradient, and this is G by Cp. And here the density profile goes as this. So alpha is basically the adiabatic index, and the criteria for convection can be found out by Schwarzschild criteria. So for that, this gradient should be greater than the adiabatic temperature gradient, and that we can measure using this parameter called superadiabacity. So this is a normalized parameter. And also another criteria is the Rayleigh number should be greater than the critical Rayleigh number. So these two criteria, if the system validates, so they will start, it is unstable to convection. So we can non-dimensionalize our system. So the length scale is non-dimensionalized by the length of the box. The velocity scale is non-dimensionalized by the free fall velocity. and the temperature and density is non-dimensionalized by the bottom reference temperature and density. And we have these control parameters. So there are 5 control parameters. First is the gamma, the ratio of specific heats. Second, that I have discussed, superadiabicity. So third is this dissipation number. So this is nothing but the G by Cp, that adiabatic temperature gradient in the non-dimensionalized part. And this D corresponds to the density contrast. So if it is close to 1, then the density contrast will be very high. If it is close to 0, the density will be constant. And Rayleigh number and Prandtl number. So we wanted to simulate this system where we fixed all the parameters and changed the Rayleigh number. So we have fixed gamma to be 1.3, epsilon to be 0.1, and D is 0.5. So this D 0.5 corresponds to around 10 density contrast. If the bottom is 1, so the top plate will have 0.1 density, and the Prandtl number is 0.4, and aspect ratio we have taken to be 4. And we have used, so I have developed this code. So this is a finite difference Python solver called Dhara, and we have also scaled it in Frontier. So we have scaled it up to 1024 nodes, and Frontier is the fastest supercomputer right now. So it has AMD MI250X GPUs. So this is scaled in GPU, and this is a GPU plus CPU code. And we use CUDA kernels in between to fasten the finite difference part. And also the single GPU performance is around 200 times compared to the single core of AMD EPYC 2543. So these were run on Argonne National Laboratory supercomputer Polaris, and the highest 2D grid is 16,384 by 8,192 for 2D, and for 3D it is 900 square by 450. And for this run, it took around 1 week time to go till 100 free falls time scale. So there is a movie for 10 to the power 12 number. So this is during the steady state. So we can see actually the turbulent Mach number. So the maximum turbulent Mach number goes up to 0.5. And one more thing in the system, this is asymmetric in the z direction. So the plumes that rises from bottom, they come down very fast, sharply. So there is a negative kinetic flux downwards. And also we can see this from the density. So these are subtracted from the adiabatic component. So this is T minus TA and rho minus rho A. And these are the field plots. So I have plotted this for 10 to the power 12, 10 to the power 15, and 10 to the power 18. And we can see, so this is the bottom boundary we have zoomed. So this is for 10 to the power 12, it is around 10 to the power minus 3 of the order. I think 3 into 10 to the minus 3, and it decreases as we increase the Rayleigh number. And this run actually 10 to the power 18. So we need to resolve it more, but there were very few points in the boundary layer. But for 10 to the power 15, we got around 10 points in the boundary layer. So this is at least resolved. And for 3D, we have gone up to 10 to the power 12. So this is the 10 to the power 9 field, and as we can see, so when we increase the Rayleigh number, these structures get finer. So first, I'll talk about the Reynolds number scaling. So Reynolds number is defined as U d by nu, and this is U is U RMS. And if we non-dimensionalize it, so we can write it by square root RA upon PR, and this non-dimensionalized U RMS. So this scaling we can see from the momentum equation. So in the momentum equation, the pressure gradient term, the volume average pressure gradient term at the steady state, this is actually very closely equal to the gravity term. And if we, it is shown here, and if we take take the difference, so this difference is very closely equal to the nonlinear term. And from both of these, we can actually find out the scaling by dimensional analysis. So this Reynolds number should go as Rayleigh to the power half, which we see in our simulation. So up to 10 to the power 18, this matches very perfectly, and this URMS is mostly constant for all the Rayleigh number, means it does not change. So there is a Rayleigh here. So half. And similarly for 3D also we get similar kind of scaling around 0.47. And for Nusselt number, so this is the energy equation, non-dimensionalized energy equation. So there are many kind of fluxes. So this first flux actually is the kinetic flux, this one. Then there is a convective flux, and this is the conductive flux, and this is the viscous flux. So to define the Nusselt number for this system, so and to match it with the RBC Bosniak approximation, so what we did was we subtracted the adiabatic profile flux from the total flux upon conduction flux minus the adiabatic flux, and from that we find the Nusselt number to be this. So it contains two terms, and there is no viscous term here because we are dealing with large Rayleigh numbers, and this term is actually the convective term, and this term is the kinetic term. So I have written it 1 plus nu convective plus nu kinetic, and this kinetic term is negative because of the asymmetry. And another definition we can use it using the boundary is at the bottom or at the top we can find the gradient of this theta. Theta is nothing but T minus TA. So and average it over the area and time. And similarly for this is the average over volume and time. So then we can find the Nusselt number, and we have averaged it over several orders of this free fall time scale. And what we find is up to 10 to the power 18, like we get a pretty nice scaling of 1/3 in 2D and also in 3D, and both are very similar. And this kinetic flux, especially in 2D, it increases after like this around 10 to the power 16. This one, and this we can see that from this equation, convective Nusselt number equation. So in this equation we have a correlation here of rho uz. So this is the momentum density and theta, and if we find the correlation we see that it keeps on decreasing with around minus 0.2 power, and it does not saturate. So to get a ultimate regime, this correlation should decrease, and currently we are looking at why is it so. So we are checking all the modes and seeing if the larger modes are also showing this kind of correlation. So yeah. So in conclusion, we have shown the Reynolds number scale as Ra to the power half for both 2D and 3D, and also the Nusselt number shows classical 1/3 scaling till 10 to the power 18. This 10 to the power 18, I will say around 10 to the power 15, it is very accurate, but we are running for higher resolution for this grid, for this run, sorry. And for 3D up to 10 to the power 12, it is showing this half classical 1/3. And also we expect the scaling to remain classical for even larger Rayleigh number. And for the future work, so I have already talked about this, we are studying these modes and correlations, especially the starting like 10 or 20 modes, and if they also show this minus 0.2 scaling, and also analyze the boundary layer, so if the log layer is actually present or not. So we have submitted these results, and it is in physical review letters, and it is under review. And I also thank Argonne National Facility and Param Singnak, the HPC system in IIT Kanpur, for providing us with computational time. Yeah, thank you.
Hi. When I think about convection in the atmosphere, I think of it sort of heated from the bottom and then going into a stable stratification, and similarly for the ocean, cooling at the top and going into a stable. Whereas when I think about the Rayleigh number, it's heating at the bottom and cooling at the top, right? So it's, just can you comment on the difference between those two problems? Because I'm not sure what relevance really the Rayleigh-Benard problem has for the atmosphere and ocean. It's just to get you to comment on that.
Actually, we were looking at the solar convection. So we were not looking at the atmospheric convection. So all the parameters that we took are for the solar convection zone. But this kind of system can also be applicable to the inside of the Earth, like outside the mantle, and also maybe in the atmosphere. But actually, yeah, atmosphere has a different symmetry.
Be negative, right? I mean,
Yeah.
you know, so there's no convection, right? I mean, the warm air is at the top, right? It's potential temperature difference, right? Yeah.
It's kind of like stably stratified in the atmosphere. Yeah.
Say that again, sorry.
It's kind of stably stratified in the atmosphere. It's not this
Yeah, it's
RBC
stably,
kind of thing. Yeah.
yeah, right. So,
But this result, mostly we were looking at solar convection. So what happens in the solar convection is, so the
Okay.
density is always greater in the bottom and lesser at the top, and also the temperature is also greater in the bottom. So there, this kind of system is applicable. So these roles are present.
and again, it's a potential density,
Yeah.
right?
It's a normal density.
Well, I mean, surely the pressure matters, doesn't it? I mean, well, I mean, it's not just the temperature difference. Your epsilon had a compressibility term in it, right? So it's kind of, you know, it's the sort of potential temperature difference between the top and bottom, or the potential density difference, really, that matters, isn't it? For defining your Rayleigh numbers, there's a delta T, right?
Yeah, that delta T is actually positive for Sun. So it is bottom, means delta T is, if we take TB minus TT, so TB is always greater than TT. The top is always has the less temperature than the bottom. So we can define this kind of system in the solar convection zone.
Okay, thanks.
More questions?
Utilization scheme which is used in the differential equation solution, that is only FDM or another scheme or some coupled scheme is used?
So the scheme was McCormack scheme, and there is a TVD correction. So total variation diminishing. It puts a limiter on the on the each step. So like it will not blow up the code, because these compressible systems, they will be very dispersive. We need a limiter kind of thing.
Yeah, actually I am asking because you mentioned in a slide that is only FDM was written. So
it's a finite difference code, yeah.
Okay.
Hello. Yeah. I was just wondering, if you are essentially doubly periodic, why don't you use pseudo-spectral methods? Why finite difference and not spectral methods?
I did not get you.
So why do you use finite difference when, you know, in a doubly periodic case you could do pseudo-spectral?
Oh, I see. So actually we started with finite difference, and it kind of worked. But spectral method also we had tried, and it was not very stable. So this scheme is very stable even for higher Rayleigh numbers. So if we use pseudo-spectral method and Chebyshev like polynomial for no slip, so that we had seen, but it was not giving a stable solution. It was blowing up, the energy was blowing up.
Sorry, just one more question then. Do you need to have fully compressible? Could you do an elastic on this?
I think not. In this code, we can't do it. But I think people have already done some of the simulations using an elastic.
Yeah, but I was just wondering if your classical scaling depends on how you do your compressibility, I suppose. Do you need compressible? I mean, you could just, you know.
So actually, this compressible system is more easier to solve than the normal Bosnius, because there is a Poisson solver we have to apply. So this Poisson solver will take like 90% of the time. But this system does not have a Poisson solver, so we can put the equation of state from outside, and this scheme is very stable. And it takes very less time to reach the higher Rayleigh. So around, like for the highest 8000 grid, the dt was 2 into 10 to the power 5, minus 5, sorry. So, but for the, maybe for other schemes, it will get even like lesser. It will take more time.
Thank you. Yeah, I think we can move on to the next speaker, which is online. We can thank him again for the nice presentation.